So I thought I'd do problem 17.9. It seems like a pretty representative problem of going in circles and kind of figuring out what's going on and how to use our formulas to calculate some things. So in 17.9 we have Charlie, who starts here, and I always draw a compass because I always forget. So westernmost part, he starts right here of the circle. And they run counterclockwise, which means their omega is positive. If they said clockwise, we just have a negative omega, right? But counterclockwise is the way we normally go. So their angular velocity, omega, is positive, so that's nice. Alexandra is running at 4 meters a second around the circle. We don't know how fast Charlie's going, but it takes her 2 minutes to catch up to him. Okay, so we know he's going slower than Alexandra. And then we want to know where Charlie is after 1 minute. So basically we have to use Alexandra's information to figure out Charlie's information, and then we can figure out Charlie wherever he is anytime we want. And so they say 1 minute. Okay, so first off, we're going to have to be careful with minutes and seconds. We'll just convert their minutes into seconds whenever we do math. Okay, the radius of the circle is 60 meters, so they're running around. Okay, so that's what we know, and we want to figure out everything about Charlie, so where Charlie is. Alright, so first, let's see, let's figure out, just because it seems like we should, let's figure out how much further ahead, how much does Alexandra have to catch up to Charlie? Okay, so that distance of the 1/4 circle. So she has to run that extra distance. So the distance she has to go, the distance, let's say, to Charlie, so I'll put a DC here, distance to Charlie, is 1/4 of the circle. So 1/4 of 2 pi r, which is 1/4 of 2 pi times 60, which is 30 pi. I think, yep, 30 pi. And we can decimalize that. We don't want perfect answers here. So 30 times pi, I get 94.25, let's say. So 94.25 meters. So that's how much she has to catch up to him, or how much slower he runs. And how many minutes she catches up in? In 2 minutes. So in 2 minutes she has to catch up by that much. Okay, so that's after 2 minutes. So let's say he catches up right here at 2 minutes. So I remember that. Which of course we're going to use seconds as 120 seconds. Alright, so what else can we figure out? Well, let's see. Let's figure out the distance she goes. The distance of Alexandra, so I can call that dA. The distance Alexandra goes in 2 minutes is her velocity, which is VA, velocity of Alexandra times the time. She's going 4 meters per second. And the time is 2 minutes, which is 120 seconds. So 120 seconds, so she goes 480 meters. Okay, that's how far she goes. Charlie, meanwhile, distance of Charlie, he goes 94.25, less than that, right? So she goes 480, he goes 480 minus 94.25. So he goes 480, what she goes minus 94.25. So what's that? 480, I get about 385.75. So he goes 385.75 meters in 2 minutes. I'll write that down. So in 120 seconds. Okay, well, we can figure out his velocity then. So the velocity of Charlie, he goes 385, distance divided by time, 385.75 meters and 120 seconds. So his velocity is that. So divided by 120, I get about 3.21 meters per second. So he's going 3.21 meters per second, which, makes sense. She's going 4, he's going slower because she catches up, so 3.21 seems reasonable. Okay. Now we want to know his circular stuff. So if we know his velocity, we can figure out his omega, because let's see, velocity is omega r. how fast you're going in a circle is the angular velocity times the radius, or omega is equal to the velocity divided by the radius. Put the radius over there. Yep, that's right. So his angular velocity of Charlie is his velocity v over r, which is 3.21 meters per second divided by the radius of the circle is 60 meters. All our units are right, so we should get, and this will be in radians per second because all the units cancel out except for the seconds, which means it's going to be radians. So divide that by 60, and I get 0.0536 maybe. So 0.0536 radians per second. That's his angular velocity. Okay, now we can write down where he is at any time we want. So, as we remember from earlier, the x position of someone going in a circle is the position of the center of the circle plus the radius times the cosine of omega t plus their starting angle. And then their y position is the y center of the circle plus the radius, then it's sine, not cosine. Y is always sine, x is cosine, so sine omega t plus theta 0. Okay, here we're going to put, because we might as well, put the center of the circle at 0, 0. So x0 equals y0 equals 0, because why not? Why put the circle somewhere else? So we'll have the origin at the center of the circle. So those are zeros, that's nice. The radius is 60, and omega is 0.0536. T, we'll make sure we have that in seconds, because that's in seconds. And theta 0 is the starting angle. Well, he starts right over here. This is 0 degrees, right? And so he goes all the way to here, which is 180 degrees. That's his starting angle, or we want radians, so that's pi. So theta 0 is equal to pi. Okay, his starting angle is equal to pi, because we always make this, sine and cosine are pretty much defined to be this is 0. So if you start somewhere else, that's the theta 0. And omega is positive again because we're going counterclockwise, so that's positive 0.0536. Okay, now we can figure out any time we want. So his x position, that's 0, is 60 cosine of omega t, and I'm going to write in the omega. Omega is 0.0536, 0.0536 t plus pi. That's his x position anytime we want. They say they want to know where he is after 1 minute. So t equals 60 here. So in 1 minute, then that's equal to 60 seconds, which is equal to t. So we just plug that in. So 60 cosine of 0.0536 times 60 plus pi, and that's equal to, now here's where you got to be really careful, make sure your calculator is in radians mode. When you go, you're going to figure out what this is, take the cosine of it, it has to be in radians mode, and multiply by 60. Okay, so that's 60 cosine of, let's get the stuff in the middle there, so times 60 plus pi. I get 6.356, and that's radians, so I want to make sure I have my calculator in radian mode, and then times 60, and I get about 59.8. So he's at about, his x position is 59.8 meters, and then his y position is 60, everything the same except sine. So everything is the same except sine, what's inside here is the same. Omega t plus theta 0 is the same. So we can just say 60 sine of that, 6.356. Save us some time. Sine times 60, and I get 4.365. So 4.365 meters. So those are his position, where he is. His x is 59.8, y is 4.365. So we're saying the center of the circle is 0. So his x is 59.8. That's almost out pretty far, right? He's almost right here. Y is 4.35, so he's a little bit up. So he's somewhere right about here, only 4 meters up, 4.365 meters up. My circle's kind of bad. This should be the furthest over. He's somewhere right here. All right, my circle went outwards there, but see, so that's where he is, somewhere right about there, just past what we call the 0 point. Okay, so that's how you do these. It's kind of a puzzle. You just start writing down things you know, well, like the distance from here to here, and use our old formulas, distance is velocity times time, and you just kind of play away with it. It's always important to draw as good a picture as possible so you can really think about what's going on, what's happening in here, and just start writing down things that you can figure out, and then usually a solution, you start seeing how to do it. But you know, that's, again, draw a really good picture, just start writing down what you can figure out, and then hopefully something comes to you for how to solve that, and then using our old formulas, V equals omega r and stuff, and using these here for the positions where you are at certain times. Be really careful with units, so it's mixing seconds and minutes. Sometimes they tell you revolutions per second, so you got to convert revolutions to radians. Remember, revolution is 2 pi radians. And make sure, again, minutes and seconds, keeping all that straight. So hopefully that helps. A lot of the problems are similar to this. You just have to, again, really be careful and draw and figure out exactly what's going on. Okay, thanks for listening.